Okay, we're going to start now with sailing and astronomy. The use of astronomical positions, the sun going through a particular notch in a building, and other kinds of different kinds of sticks, viewing the length of the shadow at noon. That's the fact that the Earth is a sphere. And there was a North Pole star. Thus, latitude was longitude was easily determined. If the pole star, Sirius, was directly overhead, then you were at the North Pole. If Sirius was at the horizon, you were at the equator, a separation 90%. So whatever angle measurement determined the longitude of where you were currently located. A device that was created was a sextant. A sextant is an instrument that has two mirrors that reflect two different portions of between two different objects. And there's an angular measurement device between those two. So you can see a sextant to use it to measure the angle between the astronomical object, such as a star or the sun or something like that, and the horizon for the purpose of celestial navigation. The estimation of this angle is known as sighting a sextant. The angle and the time when it's measured can be used to calculate a position line or a aeronautical chart. Sighting the sun at noon or Polaris at night estimates latitude. This is a sextant. You can see that there is a way to move one of the two arms along with the device in the center. So this can be loosened and moved up or down. And the two things that you're looking at give you the information about the angle that's measured and tells you what the angle is that you can use to tell you relative to the Earth. Longitude was a different matter. You needed to have clocks, and clocks didn't occur until considerably well after Galileo. You can imagine a pendulum on a boat is just not going to work. So eventually spring types of chronometers were developed, and they had reasonable stability, initially 10 to 15 minutes a day, later 5, then 1, and today we do much better than that. But even at a couple of minutes, sailors had the ability to navigate pretty well. However, the time we're talking about is local to some prime meridian. And early on, there was Greenwich, Paris, Berlin, places in the U.S., all kinds of places. So sailors and people who were doing geodesy measurements were all doing it relative to longitude of some particular prime meridian in their country. So what we're talking about is something called sidereal time. It is a astronomical construction that astronomers use, and the places where people had clocks in Europe generally had multiple ones on any major building. And an example is the Tower of the Island in Geneva, which had 3. A big clock face in the center showing Geneva time. The face on the left showed Paris time, about an hour less, and the right one showed Bern time, about 5 minutes more than Geneva time. The uncoordinated chaos of time caused European military and commercial interests to demand coordinated time. Once train transport became dominant, crossing borders, the mercantilists just eventually called upon for the choice of a single prime meridian. It took a major European convention that, by having Germany and the U.S. side with England for France and France's prime mission, can't think of the word, but he was the person who France sent to the convention, and they eventually had to submit to Greenwich prime meridian as the standard for the world. Even though Poincaré, in his tremendous amount of engineering, learned or developed how to have electrical connections that were almost or about 2/3 of the speed of light, and they were able to do what he thought was simultaneous, because, of course, you could figure out when you knew where you had gone the change between the time that you started any place to any place else. In this, up until this coordination, sidereal time was computed as an astronomical observatory. So there was physically a observatory near each major location, and it was Poincaré, as I said, the great engineer, who created electrical connections to determine, quote, simultaneous time, but he was not able to think of it as anything but Newton's simultaneity. There's a very interesting book that I'm willing to recommend to people. And it was called Einstein's Clocks, Poincaré's Maps, Empires of Time. And it focuses on Poincaré and simultaneity, and then the dramatic change about Einstein and special relativity in his Annus Mirabilis. It also talks about the stability or chaos associated with the orbits of the planets around the sun, but we're not going to talk about that in our meeting here today. In 1905, Einstein created 4 papers. The first we know is the start of quantum mechanics on a heuristic point of view about the creation and conversion of light. This was the idea of light being quanta. The investigations on the theory of Brownian motion, which was actually a proof that atoms existed and were finite in size, and on the electrodynamics of moving bodies is what we typically call special relativity, although later Einstein was sad that it was called special relativity. He thought it should have been called invariance. And lastly, the most known equation in physics is m equals E divided by c squared, and that's the one that the 4th paper gave. Does the inertia of a body depend on its energy content? So these were an amazing set of papers that are every much the equivalent to the work Newton did in 1666, laying the foundations for much of physics and mathematics. So I'm going to stop now and ask if there are any questions.